Okay, good morning everyone. So till to date, we have completed the single degree freedom system, pre-vibration, post-vibration, damped, undamped, and we have also seen how the different types of forcing function can be used in terms of Duhamel integral. We have also seen, and we have also studied the D operator in a quite extensive manner, so that most of the functions we can able to solve. So now, however, there we have seen once we are solving that using Duhamel integral, as well as in case of the D operator, we have seen there are some limitations, because in case of D operator, you need to approximate your function with such a way that you will get the complete function. Then only you can able to solve it. If you are not able to get that complete function, it will be difficult for solution of the complete thing. So so that is one challenge associated with that integral process. On the other hand, in case of Duhamel integral, we have seen that there are some portions, like for example, if I just go back to the previous lectures, so we have seen that once we will do this Duhamel integral type case, we have seen that sine omega dt is there, so it is very easily we perform, that is a undamped oscillation, but and also the magnitude is constant. But once we will have something damped and also the function is itself is varying, then we see that it will be something like a integral of the product u v z or something like that, like a 3 parameters need to be integrated, so that will become very complicated. So that is also, we can see, not that effective method which can be very nicely used. Okay, so but in the real life, we are studying this subject also to solve or to able to be solved for different types of the systems which what we are encountering in our real life. So the question comes that, okay, then how, what should be the best way to do that? So there actually comes the picture of numerical integration schemes, or like a numerical methods. So in today's class, we will start to look at how the numerical methods will work and how we can able to get the solutions from that. Okay, so that we will study primarily from the today's class. Okay, so let's see. So now if you see mx double dot so this is the way how we can able to write the equation of motion subjected for the earthquake. Okay, so first let's see how we can able to write this one, and then we will go into the numericals one. So suppose you have a system, a single degree freedom system, and let's say you are exciting the base with UG double dot, because if you see any earthquake excitation, you will mostly see the plots are like this way, that acceleration versus time. You will have some plot like this. Plot you will see. Okay, so it is actually showing how the acceleration of the ground is changing with time. Okay, so you will get several plots. As we were discussing in the last class, we can have around 4,000 5,000 data points for a single earthquake, most of the cases. So in this case, so now you are applying that at the base of the motion. Okay, so what is exactly happening at the base? So if you see that that is my structure. Okay, now, so that was my main system. Okay, once it hit by earthquake UG dot, so it get shifted by amount of UG. So this also gets shifted by amount of UG automatically, and then it start deflecting. So that is my X. Okay, okay, no doubt on that. So if I start writing the equation of motion, the acceleration will be mx total double dot plus. Now if you think how much is the inertia of how much is the elastic restoring force, because if you see the column get deflected only by x amount, not by xg, because base is shifted by xg. Okay, so the strain in the column is proportional to the deformation in the column, so that will be only x into k into x, and automatically damping will be also this much. Okay, now your x total is nothing but x plus ug. Make sense? So if I just substitute that here, so instead of x, if I just put the x total here, so I can write it x equal to x total minus ug. So I can write it m x double dot plus k into x total minus ug plus c into x total dot minus ug dot, that will be equal to 0. Okay, or else, so that is like one way to write the equation of motion, or else we can write m into x plus ug double dot plus kx plus cx dot, that is equal to this. So I can able to write mx double dot plus kx plus cx dot equal to minus mug double dot. Make sense? So this means what? So my x is the relative to the ground, not the relative to the original, that is not the absolute. So xt is the absolute frame, xt is the absolute. Okay, x is relative to, and ug is the ground displacement, and obviously the ug double dot is the ground acceleration. Okay, so this tells what? So we can think that once we have this type of thing, we can say that okay, now I can analyze the system assuming that the base is fixed and the force, which is minus mug double dot, is acting on the structure. That we can say from this, because this is nothing but a force. What we were solving before? We were solving mx double dot plus cx dot plus kx, that is equal to force. So if you see, there is no difference between the minus mug double dot with a force. That is exactly similar type of thing, and this way we can able to find out what should be the force from the ground, means once the system is subjected to a ground motion. Okay, any doubt on that? And please remember that this x is measured from the base of the structure. Okay, clear? No doubt. So now let's try to see that if we are having this type of different values of the ug double dot, how we can able to solve it. Okay, so mx double dot plus cx dot plus kx, that is equal to force, or that is equal to maybe minus mug double dot. So if that is the case, in that case, so we will try to solve it using the numerical integration scheme. So we know, so now what we can think, that is my full time domain, and we will have some points in a certain interval. Maybe these are like a delta t, or maybe you can say h. So after that certain interval, we will have the different values of the forces or the different values of the ug double dot. and our objective is to obtain what are the values of x, x dot and x double dot for those steps. Okay, so now we know that this equation of motion is a ordinary differential equation of second order. So how should we solve it? So in that case, the first thing in any differential equation comes in mind is the Euler's integration scheme. That is the first differential method what people have used. So what is that Euler integration scheme? Anybody remember? Not exactly. Euler integration solution is actually in the numerical integration. Euler scheme is telling, like suppose you have something like you will have dy dx equal to f of x comma y, maybe. That is primarily a first order differential equation. One thing very important, all the numerical schemes are specified for the first order differential equation. Now the biggest question comes that we are dealing with a second order differential equation. What to do with that? That we will see throughout the lecture, that how we can able to encounter our case, because we will mostly deal with a second order differential equation, because once we are considering the inertia, it will be multiplied with the acceleration, and which is a second order term of displacement. So we will have to deal with the second order. So dy dx equal to function of fx. What does that mean? That its slope, we are giving the solution of the slope, that how the slope of a equation is changing with its path. Okay, so somewhere it can be defined. So what can we do? So we can say that like a y can be written as yi, so that is yi plus 1 can be written as yi plus dy by dx. So that means what? Very simple manner. You are in this point and you know what is the slope at this point, and you try to think that okay, your solution may be going somewhere like this, but you don't know how it goes, but you know how much is the slope you are having here, and from there you are predicting that okay, my solution will be somewhere here. Make sense? You know the slope, you will just tell that okay, that is my gap, so the solution, next solution will be here. So this method, so you will predicting somewhere here. So that is your prediction, that is the predicted value, and that is yi plus 1 you will get, and that is maybe the original function of y that you don't know, can't do anything, because that is not known. Means once we see the graph, then we cannot plot it. Actually we will not have that graph, and then we have to start plotting it. Therefore that approximation will be coming into picture. Okay, so this type of things are happening. So in this case, so now this is known, this we are getting, okay, perfect. So there is definitely some error, and if you see, most importantly, we are try to getting the solution at yi plus 1 from the previous steps data, or maybe from the current step data. We are trying to forecast what will be the value of the next step. Okay, so like we are at ith step, and we are forecasting for I plus 1th step. Get that point? We have no information about I plus 1th step. None of the states are known for I plus 1th. We have the displacement data of the ith step and also the velocity data for the ith step, and from that too we are proposing what should be for the I plus 1th step, and that thing is known as explicit scheme. this type of scheme where we are proposing or predicting the value of I plus 1th step without having any of the state defined for I plus 1th step, that type of schemes are known as the explicit integration scheme. Okay, that is one of my very favorite question I asked during the PhD interview and all those, that okay, please tell the difference between explicit scheme and implicit scheme. Okay, so and also like several cases, like those companies, those who are working with the finite element or maybe working with the simulations, that is also very favorite question for them as also. So difference between the explicit and implicit scheme. So this is an explicit scheme. So automatically, so if I just give you an example from the real life, what is this type of scenario? Like for example, we are forecasting the temperature. Okay, we more or less try to see that okay, what is the more or less temperature gradient. We are here in Delhi, and maybe we take a forecasting for, let's say, in Simla. So we are not using any data of the Simla. We are just having the data of Delhi, and we have some sort of like a gradient in India, that okay, how the gradients are working, and we are trying to forecasting how much should be the temperature of Simla. So there you can automatically understood the chances of error could be significantly high, because you are not using any state of that location or that time. Because here I give the example in terms of space, but here you can think it just changing it to the time, that how the different states of the time are actually working. Okay, so that point actually need to be considered. So therefore we can see that explicit scheme may have some error. So how we can able to mitigate that? We should not jump too much. Don't try to predict from here to Simla at a go. Predict maybe 7-8 point in between, so that your prediction will be much more much better, and you will get some reference point, and therefore your error will be minimized. Like for example, if you see here in this graph also, so like let's say that is your graph originally goes. Now if you start like try to calculate the slope at this point, so you're okay, you got that slope, and now if you start predict, take the h for this much, so that look, you will predict it here, because it will just go. Whereas if you take your slope, I mean if you take your displacement up to, I mean the gap up to this, then you will predicting here. Now you see the differences will be less, and again you will calculate your slope at that point, so it will be somewhat coming like this, so your solution will go. So if you reduce the time step or increase the number of the time intervals, like how many intervals you are taking, then your solution will improve. And all the explicit scheme has certain upper bound, after which the solution will be like it will just blow up. You cannot able to get a convergence with that. So that will be stability issue will come into picture. Okay, so these things are associated with the explicit scheme, because you are not using any of the state information of I plus 1th step. You are just calculating from ith step or I minus 1th step to forecast what will be the response of the I plus 1th step. Okay, so Euler's integration scheme is the more or less, you can say, the first type of like integration scheme which was there for a first order differential equation. Okay, it is very problematic to use for that first order differential equation integration scheme for our problem. I will show you that how we can write a second order differential equation into the two first order differential equation. not a single first order differential equation, we will have two first order differential equation. That we will also come into picture. Okay, maybe I can just show that first, maybe, why not? Okay, so then first try to go for that, how we can make it like a single equation into the two first order differential equation. So like this equation is one of my equation, fine, and second equation I am just assuming x dot equal to x dot. Very crazy, and it is always true, x dot will be always equal to x dot. There is no doubt. And now how will I write the two equation combinedly? That is the most interesting thing. And you have to use always x dot equal to x dot. You cannot use x equal to x or x double dot equal to x double dot. You have to always use x dot equal to x dot, because I will show you why. If you see now, you have here, so first equation, if I start writing it from first equation, I can able to get x double dot will be equal to minus c by m x dot minus k by m x minus ug double dot. Okay, I just divide by x and I take x double dot in one side. Okay, so that become maybe my equation number 3, and I have my equation number 2, x dot equal to x dot. That was my equation number 2. So can I say my x double dot and x double dot and x dot as like a matrix form? So this one will be x dot and x plus some force. So here, what should I put? Okay, I got my matrix, and here we will have ug double dot and here 0. Okay, so we can. So now if you see, this is my dy dt should be equal to a times y plus some constant. So try to understand the philosophy of it. What I try to do? We try to do that, try to make this dy dx term at the left hand side. How we can able to get dy dx terms at the left hand side? We must have the maximum order of the differential equation. So which one is that? X double dot. So we keep x double dot in the left hand side and we take everything to the right hand side. Okay, now x double dot is there, so it must have another, it's just lower version, so that is x dot. So that's why I told x dot equal to x dot is the another equation. You can always take x dot equal to x dot, and you see that second equation x dot equal to x dot will allow you to have that second form of equation what you can able to put here. So in the right hand side, once you are getting, you will have, sorry, left hand side you will have x double dot and x dot equal to, now you are started clubbing that full thing, keeping the mind that you have first dy dt, then you will have a y term. So what is the dy dt? Dy dt was x double dot and x dot. So what will be the y? X dot and x. So look, x dot and x. That is the two important thing, these two things. And rest of the thing is that how you are arranging the matrix form. Okay, so you have to keep in mind that you have to bring these two terms, means two vectors. After all those things will be automatically done, not a problem. You have to just rearrange it. So automatically, like if you make a mistake like this way, that you put it x double dot x dot equal to, suppose you have written it here x and x dot, sorry, that will not work, because you see its derivative is not this. You got my point? So you have to find out that y, so that y's derivative will be the left hand side, so that you will get the Euler's equation that dy dx equal to f of x comma y. Because Euler did not told that his equation is only applicable for the scalar values. It can be done for the vectors also and matrix also eventually that. So y can be a matrix, a vector in that case, and f of x comma y become a matrix and multiplied with another vector plus a vector. Okay, so automatically you can understand that become very complicated, because now you are not having a single slope, you are having a two slopes, actually four slope, because that full matrix become a slope matrix. Okay, so obviously these are getting complicated. Okay, so this is the Euler's integration scheme, and due to this type of complexity also sometimes we like, and as well as this solver need to be very much specific. Like for example, you have to use a particular like your time step should be very small and all those things are there, and it may also quickly blow up as well. But this is the very fundamental solver, very fundamental solver. Like once you will suppose if you develop some schemes, then maybe you will prefer first to extend on the Euler's integration scheme. Like we have developed our one solver for the impacting problem. Like suppose if there is some impact happening, then how we can able to solve the full system, because during the impact your solution and schemes need to be changed. So there we have developed one linear complementarity based problem, and that portion we will put in the Euler's integration scheme. So that new solver what we made fundamentally was the Euler's integration scheme, and after that we will implement that portion. So these things you have to keep in mind, because this is a quite nice solver to make much easier to go with. Because suppose if you try to change the Runge-Kutta solver or something, much difficult, whereas modifying the Euler integration scheme is comparatively easy, because it's a very simple solver. Other solvers you will see like getting much more complicated. Okay, so there the modification will be quite challenging. Okay, central difference scheme. So here what happening, you have y, so actually y I plus 1 means y of t plus delta t. Okay, so this thing can be written in form of the Taylor series expansion. Okay, so in Taylor series expansion what we are doing, what is the basis of the Taylor series expansion? So if you see, once we have this type of scenario, we will basically do like this: y of t plus delta t into dy dt plus delta t square by 2 into d2 by dt2 plus, I think, factorial 3. Yeah, factorial 3. Yeah. So this is the Taylor series expansion of that. Okay. So now you can say that y I plus 1 equal to this Taylor series expansion. So what will be y I minus 1? So y I minus 1, that is equal to t minus delta t. So you are just writing it here. That will be minus delta t into dy dt plus delta t square by 2 d2 by dt2 minus delta t cube by 3 d3 by dt3, like this. Agreed? Now what can I do? Add both the thing. And also if you see okay, so just like try to add that two up. So these two will be cancel out while we are adding them up. These two will be cancel out by each other. Okay, and these will be also cancel out because they become the plus and minus. So this one will become delta t square into d2 by dt2. Okay, any doubt? No doubt. Very good. So this term is acceleration. This term is acceleration. d2 by dt2 acceleration. Okay, and other thing is this, so I can also write it 2yi plus this into maybe y double dot I, yi double dot. Okay, so this can be written as yi double dot equal to yi plus 1 minus or plus y minus 2yi divided delta t square. Can I say that? So that gives the basic Euler integration scheme. Okay, now if I start implementing it in my equation, that mx double dot plus cx dot plus kx equal to minus mug double dot. So try to write it for ith step. What will be the equation? M I plus c xi dot plus k xi should be equal to ith. So that is the ith point, how much is coming. Okay, so obviously you can understand that y and I can be interchangeable because here I just show it as like a scheme, and obviously it can be x, it can be y, it can be z, whatever you put, doesn't matter. Okay, so we can see that whatever is yi comes, we can put it here, not a problem. But what will happen with the xi dot? Because these can go here. Okay, what about this xi dot? We can also need to also find it out. How to do that? Let's see. In the last case, we have added them up. Now subtracted them. So what will happen? Yi plus 1 minus yi minus 1. That one will be, first portion will go, and second one will remain 2t into yi dot plus 2 into t cube by 3 factorial into I triple dot. So yi triple dot, that is, suppose if I thought in terms of displacement, triple dot of the displacement is, yes, someone jerk, yeah. So we may consider that way, or in some case we may ignore that. We may say okay, no need, forget it. That is also fine, no issue. So like, because that jerk you cannot able to calculate directly, so some of the cases people may forget that also. Okay, so if you ignore, so ignore it, and so that we can get like here also, if you see, after that the terms will be coming. In the first case also like after these the terms are started coming, like all the odd terms will be there, or maybe the even terms. Yeah, even terms will be there, and here all the odd terms will be there. So you have to truncate at certain point of time, that okay, I will not going to consider after that. And also another important point is that your delta t is supposed to be a small value. So suppose for a earthquake case, generally the time step on which the earthquake motion is recorded, that is 0.01. Okay, so you have data for 0.01. So definitely you will not going to solve it less than 0.01. That make no sense. Maybe you can go finer of it, but you will never use more than that. Okay, so if I think that maximum delta t for a earthquake case is become 0.01, now think what will be that 0.01 cube. So how many zeros? No, 0.01 minus 6, 10 to the minus 6, so it become like a millisecond. So whatever the jerk value is coming, it will be multiplied with 10 to the power minus 6, so automatically the value will be negligible. So that's why we start neglecting that point, because delta t is very small compared to 1. There is some sort of like a 2 or 3 order of magnitude. So definitely it will, we can easily able to ignore that, because unnecessarily otherwise our life will become very problematic, like we are taking so many terms. Okay, so I think we are having this like yi dot equal to this much. Okay, so now we can substitute this portion here. Okay, fine. So now if I try to write the equation of motion, then how it can be? So xi plus 1 minus xi minus 1 2xi divided by delta t square plus c into xi plus 1 minus xi minus 1 divided by delta t, 2 delta t plus k into xi, that will be a mu g double dot I. Okay, so suppose if I start taking all the xi plus 1, xi and xi minus 1, so let's see, m by delta t square plus c divided by 2 delta t into xi plus 1 plus, or rather minus 2m delta t square x 2m delta t square plus k xi minus plus m by delta t square minus c by 2 delta t xi minus 1 is equal to a mu g double dot I. Get the point? So how will you start solving that? Simple. What will I do? I will just take that plus sign, equal sign here. So this one will become minus, I just multiplying with the minus sign. So this will become minus this with this. So you can see that for I plus 1th step, to find out the solution for I plus 1th step, you need the solution of the current step and the previous step. And this is known for all the steps, because that is your input acceleration or input force, whatever. Okay, any doubt in that? Yes. Very good. So initial time, if you know that means first you put I equal to 0. Very good. So in this case it will become like x0, because this thing is known to us. Wait a minute, just let me first mark. This thing is known to me, m is known, c is known. If I also set delta t, then the full thing is known. Agreed? Next one, m is known, k is known, delta t is known, so this is also known. This is known, this is known, this is also known, this is known. Okay, and this is completely known for 0 to whatever the stage we are taking. Xi, yeah, first one, like suppose for first step if we are starting, then this will be x1, then this will be -1, and this will be ug:0. Okay, so that will be my x1. Perfect. So that is a very important question actually what he asked. That is, for solving the central difference scheme, we have to give a value for xi-1 also, means x-1 step, which could be the previous of the initial condition. Generally, how we can able to calculate it? If you see, once we are solving like a second order differential equation, or maybe in this case we are generally having two initial conditions. One is velocity, initial velocity, and another is initial displacement. So that x-1 you can actually calculate from the initial velocity. Okay, that how much is should come at xi-1. From there we can able to go ahead. Okay, I will also show that how to do that one. So this thing is okay. Any doubt? Up to this stage, any problem? That how we can able to get the solution. So like suppose for example, if you calculate that, now you get all the values like x0, you get x. So now like the next step will be x1 here this will become x0, and this will become x2. So x2 once you get, go for x3, x4, x5, x6, x7. It can just, you can write a for loop, but the important point is that how to get x1 minus 1. Yes, so I'm coming into that. Yeah, so x minus 1 we can actually think from here. So if you see the that equation, so you can see that y minus y minus 1 should be equal to y0 minus delta t into y dot 0. Just if I write this equation normal, just if I expand it in the Taylor series. Okay, so these are my two normal initial conditions, y0 and y dot 0. Okay, so if you know what is your delta t, you just put that, you will get what will be your yi minus 1. So you will get xi minus 1 from that, substitute it, keep going. Make sense? Perfect. So here also your second boundary, second initial condition get used. Okay. Any question after this? So this scheme is a explicit scheme or implicit scheme? How? So what? -1 and +1. But why it is explicit? Why not implicit? Because last time we see we need only one value and still it was explicit. Here we have two values. Still is it explicit or it should be implicit? Explicit. But why? Give little bit solid reason. Exactly. I plus 1 is no information we are using. That is why it is implicit, explicit. Okay. Once we will use the information of I plus 1, yes, then it will become explicit. Okay. And also, more importantly, we are using the forcing for ith, not I plus 1th. Look, that term. MUGI, not I plus 1. So complete thing is at ith step. We are forecasting what will be the I plus 1 step. So therefore, very carefully we have to put the H value. Because if we put a high value of H or delta T, it may blow. The solution will not converge at all. There will be a small error will start coming, or not small, like quite like a large error, and then it will not converge. Everything will be erroneous. Okay, so therefore, like once you are using, like suppose for example, like once we are studying these courses, so we are supposed to use that for our real life. So for example, some of the cases we use this explicit scheme. Like for example, if you are doing some simulation in the Abacus, COMSOL or ANSYS type of softwares, there sometimes you have to perform the dynamic analysis, maybe the nonlinear dynamic analysis also sometimes you have to perform. There you generally use some integration schemes. So using those schemes sometimes ask that, okay, means you should need a proper knowledge on what type of schemes you are using, what are the underlying assumptions of it. Like for example, if you are solving any problem where it is involved like a large strain, large deformation, in those cases generally the implicit schemes will not work. Explicit scheme you have to use. Like for example, if you do a bullet shot, fine, bullet goes and hits somewhere, so those cases you cannot able to use properly the implicit scheme, so there you have to use the explicit scheme, and automatically you can understand that you have to solve it slowly. You should not take like a big time steps, then your solution will be full erroneous. Okay, because softwares are such a things, you need to know how to run it. If you do some garbage input, it will give you garbage output, no doubt about it. So you have to be careful that your input is not a garbage. You should know I mean completely about your inputs, that what you are inputting there. So like sometime I saw most of several cases like people use the explicit scheme with a quite big time steps, and solutions will, means you cannot expect the solution will going to match. Yeah, means if you are lucky the solution could match, but that's only the luck. Okay, so there is no guarantee on that, but yeah, implicit scheme there is some type of guarantee that okay, you will get the solution, but that's why it is not solving in all the cases. Because you cannot give the guarantee for all the things. So that is the problem. So now we will start the implicit schemes, that what are the implicit. So generally these two are the very popular explicit scheme, because they can be developed also much nicely and people can use that. Good. So in the implicit scheme, so in the implicit scheme, if you see, implicit scheme. So here first one is the, so there are the primarily 2-3 method, that is the constant acceleration, linear acceleration. Yeah, so these are the two, like a very initial level of implicit scheme. So what they are doing, so like suppose you have a variation, okay, no issue. It assumes that your variation from here to here, like let's say this is your ith step and this is your I plus 1th step. How in that duration, how your acceleration is varying. Okay, that assumption they are taking. In between, how it is varying. And there is a one value here, one value another, but in between, how the acceleration is changing. Okay, so in that case, yeah, so constant acceleration is also known as average acceleration or average acceleration. So suppose, for example, you are having so like suppose this is going like this. Okay, so in the first case, you will assume that your acceleration is varying like this throughout the domain. So this value will be average of these two. Okay, and here you will assume that this varies like a linearly. So so here if I just try to write x at maybe time tau will be x double dot I and here at tau, so x double dot tau should be equal to this plus no sorry delta t into tau. This is delta t. Okay, does it make sense that how much is the value at here, that is your x double dot tau. Got that point? You may feel that okay, you can able to get how it is varying. Can we really get or not? But do you have any chance that we can able to do it exactly, or we have to assume something? First of all, try to understand this is the plot of the response acceleration. Response acceleration, not the input acceleration. Means not the ground acceleration or not the forcing function. This is the plot of the response acceleration, means what you can able to get. Okay, so there you are assuming how it is varying. Okay, makes sense. So you have so you don't know that this point because xi plus 1 double dot you don't know, you know only xi plus 1 xi double dot, that you know, but you don't know xi plus 1 double dot. So therefore and now you are trying to speculating that okay, how this acceleration is getting changed. Is it like in that like I plus 1 is duration, the complete duration the acceleration is this much, or can I say that okay, acceleration is increasing linearly, that we have to. So these are the two assumptions, and here in the assumption the most important thing, we have already incorporated the response of the I plus 1 step, although that is unknown. That is unknown. X plus x I plus x double dot I plus 1 is unknown, but still we incorporate that in our assumptions. Okay, now think, if this is the case, what will be the velocity? So let's think there will be velocity. So here we will have xi, and here something will be so how will it vary? In the previous case it was a straight line. If the acceleration varies within a time domain straight line, means in a constant manner, how the this velocity should vary? increasing, exactly, linearly increasing. Simple. So what will be my uh, this one, a tau distance? Anybody? So the slope, if I see that slope will be this much, whichever is the previous slope. So V equal to, we can say, Vi plus AT, means the final velocity will be equal to initial velocity plus acceleration into time. Very simple. So initial velocity is this much plus acceleration into time. Here the time is tau. So please remember, tau is varying from Ti to Ti plus 1. Okay, that is tau only. Just for us within the time step, how it is varying. Okay, this thing. So good. So you can get that. Now, if I see the velocity here, and that will become, so this one will be how it will vary. We have a straight line or a linear relationship in the acceleration. So velocity will be quadratic, parabola, something like that. Yeah. So what will be the equation for that? So these are very simple actually. If you see, these are like a class 9th level mechanics. So it's done. Okay. So that way the velocity comes, and how will be your displacement? Okay. And here it will be like a cubic type of function, and we can get the displacements. Okay. So that we can get. Any doubt? Any doubt? Did we get the solution? Hmm? Did you get the solution? If you think that this is just the setup we made for, like as we did in the previous case for the like we do the Taylor series expansion, and we try to set up that full thing. Like for example, if you see, we first set up the full solution scheme, that okay, how it should come. Like here also, if you see in Euler, we set up that like how this thing variation is happening, but that's not the solution. Like yes, once we start plugging that full thing into, that gives the solution. Now here we have to plug that thing, and that will give the solution. Okay, so this is just a setting up, like we are just preparing the ground, not even the toss happened. Okay, so yes, so this is done. Then suppose if I write the displacement, so x of tau will be equal to xi plus Means you can purely do the integration on that and it will give the solution. Okay, just remember that you have to add the initial condition and then do the integration. Okay, do you want me to do that? It's okay, चलिए कर देते हैं. Some places seems like okay it will be better if I do it. So no issue. Okay, so suppose if you go from here to here, it will be like x of tau equal to, you just first put whatever is the initial condition, okay, plus integral 0 to tau, okay, 0 to tau, then x dot tau d tau. Now if you do it, think, oh sorry, okay na? So like this way we have to do. So you see that how the integration has to done on that. So previously also, once you are doing it from here to here, you should do the integration similar manner, like x dot tau should be equal to xi dot plus integral 0 to tau x double dot tau d tau. Okay, so it's a constant value just remain, and tau is comes from the integration. Here also the similar things you can think, the same formulation you can use, it will automatically come, because here you will have this, so this portion with this and this get twice of that. Okay, now if you do it again here, x of tau will be equal to again xi plus xi dot tau plus xi tau square by 2 plus tau cube divided by 6 delta t this much. So these are my first acceleration, then velocity, and then displacement. This is within the step. Okay, now we have to implement it for our solution, means in our equation of motion. Mx double dot plus cx dot plus kx, that will be minus ug double dot. Okay, now so let's first see one time that how the formulas looks like. Yeah, there is one very interesting point we need to notice here. Maybe just I will try to rewrite that form. Yes, just a minute. Okay, so suppose if I just write x tau was, but xi, okay, xi plus xi dot tau plus tau square by 4 okay, so that one is the solution. So this solution is like, this is my ith step and this is my I plus 1th step. In between, how the displacement is changing, this is the solution of that. Agreed? Agreed? From the average acceleration. Very good. But if you see in this equation, we will solve it either at I or at I plus 1. Generally, we do not solve it at any point. There are some schemes there people solve it, like HHT and all other schemes, they solve it for half also. But first do the simple one, then we can go for those methods. So if we think like we are doing it for either of that two, not in between, how we can solve that? So we can then think that, okay, how much is that xi plus 1? So we will be substituting what should we substitute here? If I try to get xi plus 1 from this equation, yes, tau equal to how much? Tau equal to delta t, exactly. So tau should be equal to delta t. Perfect. So xi plus xi dot delta t plus delta t square by 4 xi double dot plus xi plus 1 double dot, that I can get. Make sense? What about this one, the similar manner? Just if I just try to copy that one, okay, we get that. Now if I write this equation for I plus 1th step, what we can get? M xi plus 1 double dot c make sense? Any doubt? Very good. Now what should we substitute? This guy. Sorry, that should be with k. I substituted the xi, sorry, so that should be with k. Then we see it will be xi plus this, okay, plus m okay. So now let's try to see what we got. So here we first see that was my complete domain I plus 1. In all the previous cases we had solved for ith step we solved, but now we will solving, means we are solving for I plus 1th step. So the force whatever we are using is for I plus 1. Okay, and now let's try to see what are the, and therefore we can say xi, all the things are known because we had already solved that before. Once we are at I plus 1, we had already solved for I, that is for sure, otherwise we cannot advance. So at I we have solved, so all the values with I are known to us, like I, xi, x dot I and x double dot I should be known to us because we had already solved for I and we are at I plus 1 step. Okay, that is clear? Very good. So all the values of i's are also known. mck known, done. This is known, this is known, delta t is known. So which one is left? Exactly, x double dot I plus 1. So something with x double dot I plus 1 is equal to something. Make sense? Can you able to solve it? Can you able to get the value of x I plus 1 double dot? Yes, we can able to solve it because it's just nothing like something, just we have to divide by that and we will get that. Okay, any doubt? So once we get x I plus 1 double dot, we can substitute now it here. Look, here this is known, all the I steps are known. We can get x dot I plus 1. Again we will substitute back here. We will get that also. So like this way, simultaneously that three equations need to be solved in each point of time. Then we can able to get the complete solution of that. So we may write a for loop and we can just do that. So that will give the solution. So like how many time steps we have given, it will just calculate the solutions. Very similarly, you can do it for the linear acceleration as well. You can put the linear acceleration and it will also gives you the solution like that. Thank you.